Alrighty, hello and welcome to Lab. Tonight is just an open office hour format. There's no e-lab experiment to do. The thing that's scheduled for lab is there's a lecture to watch. It was given. I live streamed it last semester. And you'll notice when you go to the video, it says it's 3 hours. It's not 3 hours. I lecture for the normal amount of time, about 80 minutes. The reason why the video is a 3 hour stream is because I did it during a lab period. So I finished the lecture and then I stayed online in case anybody had any further questions. So anyways, you don't have to watch the whole thing. You can hit me with any questions you want whatsoever. I am here for it. So hit me up when you have any. Okay, yeah, yo. Let's see. Okay, a couple questions about the exam. First one: two isotopes. Okay, let's see. The first one has to do with two isotopes finding the mass. The other question. So just I'm not exactly sure what your question is, but totally hit me up. I'm here and ready. Okay, gotcha. Dude, totally no worries. I'm now we're on the same page, and that's all that matters. So here's how you handle a problem like that. So let's say that we have two isotopes, and that isotope, I'm just going to call it isotope 1, has a mass of 48.3774 mu, and a percent abundance of 44.32%, and that isotope 2, oh, I just realized I wrote isotope. Let's go with isotope. And isotope 2 has a mass of 54.8012 AMU. And I'm just making sure I'm getting my percent abundances right. I'm going to go 100 minus 44.32. All right, so this would have a percent abundance of 55.68%. And here's how you'd go about solving a problem that's asking for this. So, like we talked about in lecture, it's not enough to take an average of these two. We have to take a weighted average. And so to do that, what we need to do is we need to multiply each isotopic mass by its percent abundance as a decimal, and then add those two together. So our first step is to take each percent abundance and to multiply it, each isotopic mass, and to multiply it by its percent abundance as a decimal. To do that, you have to divide the percent by 100. All right, so we're going to do this for both isotopes, and then we're going to take a sum. All right, so let me grab my calculator. So we have 48.3774 times 44.32 divided by 100. This comes out to be 21 point, my calculator's telling me 44.086368. Sig figs wise, I'm limited here by my percent abundance. I can only keep 4, so I'm going to put 4 lines to remind myself that this number has 4 sig figs. Then I'm going to go do the next one. 54.8012 times 55.68 divided by 100. This comes out to be 30.51330816. And again, we have 4 sig figs in our percent abundance, limiting our answer to 4 significant figures. Now we take these two and we add them together. Let's see, so 21.44086368 plus 30.51330816. So the value my calculator is giving me is 51.95417184. But now we have to look at the last significant digit, and both of our numbers have their last significant digit in the second decimal place. That's where we are rounding to, 4 rounds down. So our final answer will be 51.95 AMU. So that's how you calculate the atomic mass given the isotopic masses and the percent abundance for each isotope. Let me know if that makes sense. Dude, anytime. I'm so happy to help. Thank you for making office hours a little less lonely. I was just hanging out. Actually, I was grading, and talking about chemistry is way more fun than grading chemistry. So thank you for spicing up the evening. Oh, okay. Solid. Here, let's rock this situation. All right, so we want to find the number, oops, no, let me open a new slide. We want to find the number of neutrons in an isotope of Ruthenium 96. And for this, we're going to need a little bit of help from the periodic table. We're going to locate, so the first thing actually that I want to point out is this number. So this is the isotope name, Ruthenium 96. And this number is called the mass number. And it is equal to the number of protons in the nucleus plus the number of neutrons. All right, so this is going to be part of the solution, but it's not all of the solution. We actually need to find ruthenium on the periodic table, and here it is, it's right here. And the reason why we want to locate it on the periodic table is we can find the atomic number. This number right here is the atomic number, and it equals just the number of protons. So now that we know the atomic number, we can take the difference between the atomic number and the mass number, because mass number is protons plus neutrons. If we subtract just the number of protons, actually, I want to color code this. So if we take the number of protons and neutrons and subtract just the number of protons, it's going to give us, let's see, that'll be 2, that'll be 5, just the number of neutrons. So ruthenium 96, the isotope ruthenium 96, has 52 neutrons. Oh, really? 1, 2, 1, 2. Alrighty, so yeah, so let's take a look at this name. So let's see, it is C6H10. So here we're dealing with a covalent compound, which means that we need to use prefixes for naming. And the prefix for 6 is hexa, and the prefix for 10 is deca. So the name of this compound would be hexacarbon decahydride. Weird. One, two. Okay, so I'm back. Hopefully, I'm audible. Okay, there we go. Yeah. Wow. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Okay. Let's see. Let me just double check. Yeah. Lizette, that fixed the sound situation on my end. Hopefully, it's coming through on yours. So, anyways, knock on wood, things should be good. Yeah, totally, totally. All right, so let's do. So the thing to remember with polyatomic ions is they are a group of atoms that all have one charge. So, awesome, awesome. So the thing to remember, so a polyatomic ion is a group of atoms that collectively together all have a charge. For example, hydroxide is OH with a negative charge. Sulfate for example, is SO4 with a negative 2 charge. Ammonium is NH4 with a positive 1 charge. Now, these things are just a matter of memorization. There's no other way around it, really. You just have to know what they are. The only thing you have to be aware of when it comes to polyatomic nomenclature and writing chemical formulas is when you have more than one polyatomic ion, you need to use parentheses. All right, so for example, but you name them just like you name any other ionic compound. So for example, if we were asked to write or if we were asked to name this ionic compound. The thing is, when you're naming ionic compounds, they're always named the same. All right, it's always cation name, plus anion name. All right, and here the cation name is calcium. And the anion name is hydroxide. So this ionic compound that includes polyatomic ions would be named calcium hydroxide. Like all ionic compounds, it doesn't matter how many of each is present, it's just cation name, anion name. One thing you'll notice, so let's do one with, let's find the formula. Let's find the formula for aluminum. Hydroxide. Aluminum is our cation name, and we can find it on the periodic table. It has a charge of +3. Hydroxide, we were just looking at it, it's OH with a charge of -1. Now you can see that hydroxide's charge is -1, aluminum's charge is +3, so we need 3 hydroxides to pair with our 1 aluminum. That way our overall charge is 0. And there's a right way to do this and a wrong way to do this. This is the wrong way to do this. All right, whenever you have more than 1 polyatomic ion, and this is the only twist, you have to put it inside a parentheses. All right, this tells me that I have 3 hydroxides. The reason why this doesn't work is technically this chemical formula has 1 aluminum, 1 oxygen, and 3 H's, which is not aluminum hydroxide. Aluminum hydroxide has 1 aluminum, 3 oxygens, and 3 hydrogens, because there's 3 hydroxides present. So that parentheses, whenever you have multiple polyatomic ions, is the only distinction, the only difference between naming and writing chemical formula for ionic compounds with polyatomics versus the rest of the ions. Okay, so Lizette, the final is totally cumulative. If you're asked to find the number of nucleons in vanadium-49, the term nucleon is just a generic term for any particle that's found in the nucleus. And there's 2 types of particles found in the nucleus, and that is, or those are protons and neutrons. So when a question asks you what are the number of nucleons in vanadium-49, they're asking how many protons and neutrons together are present. And fortunately for us, that is given in our mass number. So this is the mass number, which equals the sum of the protons and the neutrons present in the nucleus. So the answer is vanadium 49 has 49 nucleons. Oops. Dude, we can totally do aluminum sulfate. And that's probably as tricky as these problems get. So let's find the formula for aluminum sulfate. Now, aluminum is a cation with a positive 3 charge. And sulfate is an anion with a negative 2 charge. And here we have a real conundrum because the number 3 does not go into the number 2 evenly. All right, and so this is may look like a real puzzle. However, there's a cool trick to get to the chemical formula quickly. So we've got aluminum and we have sulfate. Here's what you do. You take your anions, your anionic charge, and make that the subscript for your cation. Then take your cation's charge and make that the subscript for the anion. Here's why this works. Aluminum has a charge of positive 3, right? And sulfate has a charge of negative 2. Well, if we multiply aluminum by 2, and if we multiply sulfate by 3, you end up getting with a positive 6 and a negative 6, and together they add to 0. And that trick, when you have two charges that don't go into each other evenly, this trick will work every time. Dude, I hope you have a good night too.